So last time we started the derivation for the heat equation, and the general idea is that we want to describe what's going on with the heat energy in a rod of length L. Here, the lateral sides are insulated, so no heat can pass through the sides of the rod. And once we've developed the model, that's an assumption we can weaken. But for right now, to build the model, we're assuming the sides are insulated. If there is any heat coming in through the sides, it would be only through the ends here. This would be the only place you could have heat stuff happening. We start with this concept of thermal energy density. And this is because we want to be able to bring integrals into it. And we want to set it up as, we're kind of describing the energy like it's a three-dimensional object, like a volume here. And so here, the energy is kind of like a mass or something that we're calculating, So the energy density, the total energy density would be just the density times the volume. And here we can take a delta X strip where the surface area is A and then multiply by the thickness to get the volume and integrate from 0 to L to calculate the total heat energy in the rod. So the other concept we want to introduce is heat flux. And the heat flux essentially represents, heat energy that's moving. In this case, our canonical definition is we assume it's moving to the right per unit time, per unit surface area. And if capital Phi is negative, then it moves to the left. Here, we just have to introduce some type of orientation. So, we would tend to be right-hand biased, so anyway. So now we want to talk about if heat is coming in, it would come in through the ends here. And so we calculate at the left, this is the amount of heat energy entering per unit time. And here on the right side, this is the amount of heat energy leaving per unit time. So here, that's where the minus sign, that's the thing here, is to notice the minus sign, because here on the right end, energy is leaving. And then we factor out the minus sign and write it in a more calculus-friendly version. Here you should think of this as kind of f of b minus f of a. In a second, we'll write that in an integral form. And then finally, as part of our model, we allow for internal sources of energy, perhaps due to the environment or chemical reactions or electrical heating, or I don't know, you should tell me. And so here again, we define the variable Q to be essentially a type of density. It's energy per volume. And so when you multiply it, it's an internal energy density, and so you multiply that by the volume, you get a heat energy statement there. So then the kind of word equation, that's the concept, here we're deriving the heat equation starting with a heated rod, but at no point does a mathematician go outside and heat up a rod, right? This is a purely conceptual derivation based on how we think heat's behaving based on our observations of the universe. And we're trying to create a model that'll mimic reality, So we're trying to just artificially create something that will act like reality based on our intuition. So, and then put math to it and make it rigorous and hopefully get realistic and meaningful results, which I think we will, because otherwise, why are we even here at this classroom, right? So the theory is the rate of change of heat energy with respect to time, in the rod can only be either due to energy flowing across the boundary or energy generated inside the rod. And so now we mathematically have expressions for, both sides of the equation. So remember, rate of change here, that's a derivative. And the heat energy we have an expression for the heat energy. So this entire side we can write mathematically like this, with the derivative, the time derivative right there. And then our heat energy flowing across the boundary, that would be due to heat flux, right? So that's this expression right here. And you should distribute the minus sign in your mind and really think about, this is the heat coming in plus the negative energy, that's going out, the term that's going out. So anywho, and then we have the internal source of energy, in the rod, and so we have an expression for that. So the rest of it is mathematical manipulation, and we start to, we cancel the area term. It's a constant. And then we combine the integral all on one side into one giant integral. So bring everything over. And now there's a little bit of analysis now. So, and I don't go into the details, but the theory is here that this integral can be shown to be 0 for any choice of A and B. And that is to say the integral isn't 0, it's not dependent on the location where we're integrating. And the only way that's possible is the integral is always 0, no matter what point you pick for the boundary, on the rod, is the thing we're integrating, the integrand, must itself be identically 0. And so that's where we come up with this conclusion. And then we move the flux and the internal source of energy back over. And so we come up with this relationship now. And so this is the beginning of the heat equation. So what the plan is now is to bring temperature in on both sides. So I want to relate this heat energy, E, to temperature. And I want to relate this flux term, phi, to temperature. Once we do that, we will have arrived at the heat equation. So now what I'm going to do is I'm going to first connect the left-hand side here to temperature, and then I'll connect the right-hand side to the temperature, and then we'll put it all together, and we will have the heat equation in our lives. And so, I will make a remark that this minus sign is a conceptual minus sign. Mathematically, the one could say, well, why don't you just pull the minus into the phi, just make it part of the definition of, but it's a conceptual thing. So here, if we assume that the heat is flowing to the right, that the rate of change is positive, and that the heat is increasing to the right, then we'd expect the heat at the right to be greater than the heat on the left side. And so more heat is leaving. And so we're expecting the heat energy to be decreasing here. So, it's a conceptual minus sign there. Okay, so now we introduce temperature. So U, the letter U here, that'll be the solution we're looking for in our heat equation. Okay, so when we introduce the temperature, this will also be the unknown in our PDE when we set it. So when we're trying to solve our PDE, we're trying to find this function U of xt. We want to know what's the temperature at any time and at any point on the rod. We want to have that ultimate knowledge of knowing at any time and at any point on the rod, what's the temperature. So this function will tell us that. So we introduced this notion called heat capacity. And so it's reasonable, of course, to, realize that the material of the rod is going to affect the amount of energy required to heat it up, right? Again, you all know better than I do, I don't know, stainless steel versus something, copper, so we define the heat capacity or specific heat, and we're going to use letter C here to be the heat energy required per unit mass of a substance to raise its temperature 1 unit. Okay, so we will either assume the heat capacity is just a function of X, the location, the physical location on the rod, or is just a constant. Initially we'll just assume it's constant to make life easy. So now an alternate description of heat energy. So the slide used to say thermal energy here, and I changed it to heat energy. I don't know that it even matters. So here, the real idea now is that we're thinking of the heat energy to be the amount of energy needed to raise the rod's temperature from 0 to the actual temperature. Okay. So suppose we know the mass density. So here rho is the mass density. Then based on this description of the heat energy, we come up with another equation for heat energy. So let's look at this first term here. Think about this for 1 second. So C of X is the amount of heat energy required per unit mass to raise a particular substance's temperature 1 unit. So when we multiply these two, this is how many units of temperature the object is at, and we're multiplying it by the heat energy per unit mass required for each degree of temperature. So this becomes the heat energy per unit mass, and then we can calculate the mass. Usual mass here is the mass density is volume, is mass per volume, and so we multiply by volume, right, and get the mass. Multiply this heat energy per unit mass, we get a separate, different equation for heat energy, which we equate to the other equation we'd established on the first slide for heat energy.
Dr. Bob?
Yeah.
Are we assuming that density is not coupled to temperature?
At this point, we are.
Okay, thank you.
And I mean, that's a fair point. That's a fair point. And so ultimately, from an intellectual point of view and from a model building point of view, I should also mention that coming up with these models, to me, it's an art. To me, some of these traditional models, it's this combination of understanding the science and the math, and it's at this intuitive level. So yeah, when you're building a model, if you start out with a model that's too complicated, then it's very difficult to make any progress or get any traction, because there's too many moving parts and it's too complicated. So traditionally, the way we build a model is start kind of with baby steps, kind of these simplistic assumptions. And then once you make progress with those, try and bootstrap them up and make them more complicated, So I think that's a great question. And, it really addresses kind of a larger issue of model building, And like I said, to have that intuition, to be able to write down a mathematical equation that accurately, or even just somewhat semi-closely describes a phenomenon in reality, like that's an art to me. That's something special, All right, I won't get too excited, sorry. So now we cancel, the old constants here, the volume on either side. We get this alternate expression for the energy density term, where what you should notice really, what have we accomplished, is on the right-hand side now, temperature has been brought into the equation, because I can now replace E up here, and we will, with C times rho times U of xt. So on the left-hand side of our equation, we've brought temperature into the story. And so now I want to bring temperature into this story on the right-hand side of the equation. So we want to relate phi to temperature. So this is a result known as Fourier's law, or Fourier's law of heat conduction. And so we have certain heat flow rules. I mean, these are essentially, results from thermodynamics. And of course, just are observing reality and saying, how does heat behave? So the first heat flow rule, which relates temperature and heat flux, is that if we have constant temperature in a region, there implies there's no heat flow. Okay. I don't know. I shouldn't say this, but think of being in a swimming pool or not. Heat energy flows from hotter regions to colder regions, right? And we just know this from living in this thing we call reality. whatever that is. The greater the temperature difference, the greater is the flow of heat energy. So think of dropping an ice cube in a bowl of hot water versus dropping an ice cube in a bowl of cold water, and how quickly, the difference there, what happens thermodynamically. The flow of heat energy will vary for different materials, even if there's the same temperature difference. And so that's reasonable. Again, we accept that there's, different materials in this universe with different densities that have different thermodynamical properties. So these four rules we can write mathematically as phi equals some constant, negative times some constant, k sub 0, which is known as the thermal conductivity constant, which will take into account the material. Could also, doesn't have to be a constant, but starting out, we're going to assume it's constant. So times partial u partial x. So let's take a second to think about what partial u partial x is. In calculus, when the function is the position function, this first spatial derivative is velocity, right? But here, u is not the position function, u is temperature, okay? So I do, though, kind of think of it like a velocity. So, in my little world, I like to think of u, the temperature, as the position on the temperature dial, So this is the temperature gauge. And this is the temperature at any time or whatever. That's the temperature u at a spot, I guess. So not u at some point x. And now if this moves, that bar has some velocity, which would be this, right? So I do sort of think of it as a position, but position on the temperature dial, on the temperature measurement stick. Do we measure temperature with the stick? I don't know. You know what I mean? And then the second derivative would be like an acceleration. Okay, so anyway, at this point, it's important to connect the physical idea and the math, So what's this saying? This is saying the heat flux is equal to, the velocity here of the temperature, the temperature change on the spatial, on the x-axis. Be very careful here. That's what's driving the heat flux. This is basically the idea that the energy difference is what's driving the heat flux. Heat goes from hot to cold. If partial u partial x were 0, if the temperature was just constant, there's no temperature difference from one point in the rod to another, there's no heat flux, where, that's statement number 1, you're at constant temperature. Okay, so as I said, k sub 0 is known as the thermal conductivity constant, and the equation, should be read as an English sentence, is that the heat flux is proportional to the temperature difference with respect, the difference here with respect to length, the physical location. And again, the minus sign is conceptual. Again, you say, well, why don't you just wrap the minus sign in with the function or something? Again, it's conceptual here. So here, if we assume the temperature, u partial x is positive, or that the temperature function is increasing, then it's hotter to the right. If it's hotter to the right, heat flows from hot to cold. If it's hotter to the right, it'll flow to the left. If it's flowing to the left, phi needs to be negative. Here, the thermal conductivity constant is assumed to be positive. So if it's flowing to the left, phi needs to be negative. We have a minus sign there. So here, the minus sign makes sense. It's conceptual, and our model seemingly fits what we like to refer to as reality thus far. And as I said, there's a lot of baby steps. We could make the thermal conductivity constant not only dependent on x, but t as well, right? I would assume the temperature would affect it as well. All right, folks. if you're willing to accept all those shenanigans and do think of the physical aspect of it, think about temperature moving and all that kind of stuff. We'll put it together now and derive the heat equation, also known as the diffusion equation. So we had our, well, if we aren't willing to accept it, Jeff, I guess it's like choose our weapons in 20 paces at dawn. No, I don't know. I don't know. But certainly I will say I didn't invent the heat equation in my defense. So we take this alternate equation for the old heat energy involving the temperature on the right-hand side. That's really the important part here. It makes sense here to me. It involves the heat capacity, which is taking into account the material. It involves the density, which is taking into account, like the mass, how much of the rod we have. And then it takes the temperature is the energy, just a description of the energy. So combine all those things, you're sort of describing what's going on with the rod, with that specific rod made out of that specific material that's a certain length and radius, And then we have old Fourier's law, which makes sense. Hot goes to cold. I buy it. And so we had our whole heat energy concept that the rate of change in the total heat energy in the rod can only be due to energy shenanigans at the ends of the rod or energy internal sources, energy, being generated internally. So now here we go. We do what's natural, plug in this expression here for E, and then plug in this expression here for phi, right? And then simplify a little bit. And now we have one differential equation, a partial differential equation, in the same variable on the left and right side that's, describing this heat energy situation. And if we can solve the PD, so here I did it right down here. So there we go, right there. Whoops. So here's this right here, and this right here. And then, here, this is a t derivative. And so the only function that's a function of t is the temperature. So we actually just pull out the other terms. Here we pull out the constant. And so here we get a second derivative here. And so here's one version of the heat equation. And for mathematical purposes, to solve it, let's just simplify it a lot. So we're going to assume C and rho are constants and that there's no internal heat source for now. And so assume C and rho are constants, Q is 0, divide K naught by C and rho, just write that, that's just a constant. So here's the heat equation that we know and love. And so I've written it in both forms, like Leibniz notation and Newton's notation or whatever. And yeah, so what you should think about is on the left-hand side, there's a time derivative. On the right-hand side, there's a spatial derivative. And here, the solution we're looking for, keep the big picture in mind, we're trying to solve for U. What's U? U is a surface. So let's describe U geometrically. U in Calc 3 terms is a surface over space, X, and time. Okay, and so now let me draw a surface. And because I don't know, I'm just gonna draw like a spherical looking thing, because who am I? Leonardo da Vinci over here? I don't know. It's supposed to be 3D. Use your imagination. It's like a top of a sphere. I have no idea. So this is U. This is U of xt. And we're talking about, time derivatives. Again, think about this, time derivatives, which would be, You're looking kind of tangent lines in this direction versus these derivatives with respect to x, right here. Here again, you know, I would remind you here that u is not a position function. So this isn't acceleration, what we're looking at on the right-hand side. But if I think of u, the temperature as being the position on the thermometer dial, thermometer stick, then I kind of think of that as being when it moves, that's the velocity, and then the, you know, the rate of change of velocity, that's the acceleration. So anyway, think about that. And here this is relating the two temperature behaviors, temperature behavior in time, rate of change in time, versus temperature as you're, you know, spatially moving across the rod. So that's what's tricky about PDEs. There's two, you know, you're evolving in time and you can pick a spot on the rod. So there's two things to keep track of, but it's just something to get used to as you're working on PDEs. So yeah, K is positive constant known as the thermal diffusivity constant. And we're looking for the temperature U of xt. We want to know the temperature at any point along the rod at any time, you know, so those are two things that we're asking a lot of. So yeah, I just want to talk about some boundary conditions now. So here we have the PDE, and because the situation is complicated and the physical situation is complicated, we can't just start solving it right away. So here I have to talk about boundary conditions, and then we also have to talk about the underlying kind of fundamental nature of the solution, because this is a solution that has to also be able to evolve in time. Okay, so we're going to have to address that issue, and I'll talk more about what I mean about that in a second. Okay, so here there's one time derivative, so we need what's called an initial, at least we need one initial condition. So here the word initial condition, you need to connect it with the time variable. This is about information that we need because of the time derivative. So your initial condition should be connected with the t variable. And then the two spatial derivatives require what we call boundary conditions. So when I say boundary condition, you have to connect that up with the x variable. It's apples and oranges is really important. So in theory, we can get you know, information about the temperature at any two physical locations on the rod. Traditionally, it's given at the ends, the left end and the right end. That's what they're called boundary conditions. And we can have different types of boundary conditions. You could have prescribed temperature, which is what you say, oh, the temperature on the left side is always 0 degrees and the temperature on the right side is always 10 degrees. You could have an insulated boundary, and we'll discuss these mathematically in a second. You could have an insulated boundary condition. What does that mean? That means we've insulated the ends and there's no heat coming in or going out. So, you know, this might be a situation where you've heated up the rod in a very hot bath. You take it out of the hot bath. You immediately seal the lateral sides and the ends. And then now we're wondering what happens to the heat dynamics, you know, based on the length of the rod, based on the material that the rod's made out of, and based on the temperature, you know, what's now going to happen. And then another type of boundary condition we have is related to Newton's law of cooling, which, as you know, is a physical result, and I'll connect everything. So Newton's law of cooling directly connects to the heat flux, and the heat flux connects to the heat equation. So we can use that for boundary conditions. So let me show you what I'm talking about. So for prescribed temperature, this is sort of the simplest type of boundary condition. You know, so we have a rod. So let me draw the picture here. So let me draw a rod. So here we have a rod, and one end of the rod is in contact with like a big metal thing with liquid in it. And so this end is getting heated up by this boiling liquid. And you can have it on the left end or the right end. Okay, so this is the fluid bath, which one end of the rod is in contact with. You can do two ends, we're just doing baby steps. Okay, so in this case, we can tell you what's going on with the temperature on one end of the rod. And so you can give a boundary condition like this. So here we're looking at this right here. So in words, this says the temperature at the left end of the rod for any time t is being described by the function on the right-hand side, which we presumably know. So this information would be known. Presumably we know what's going on with the temperature of the bath because we're controlling it. And of course, you could put it on the other end. And of course, the simplest case is to have constants. And the trivial boundary conditions are at one end or the other, not at both ends. We'll talk about what happens if you have both ends. So having a trivial boundary condition at one end or the other is the typical kind of beginner, baby step. Let's do that to figure out what's going on before getting too complicated. Sorry, the sun's coming in again. So yeah, and so for the insulated boundary, this is if we know the heat flux at a point. Okay, the heat flux capital Phi. So here we're specifying that we know how energy is entering or leaving the rod at one of the ends. And so how do we get a boundary condition out of this? Well, Fourier's law of heat conduction relates temperature and the heat flux. And so now if I know the heat flux, so now assume the heat flux is known, I can solve for partial u partial x, and this becomes a type of initial condition. I should say boundary condition, not initial condition, because this is an x variable. This is telling us on the left side, it's telling us something about how the heat, flux is, how the heat is entering or leaving. It's kind of a description of that. And so this information here on the right-hand side, we would know. That would be given. And this would be, so when it's this type of boundary condition, when it's a boundary condition involving the first derivative, it's typically called a Neumann boundary condition. And this type of boundary condition over here, where it's just the function, not the derivative of the function, that's typically called a Dirichlet boundary condition. And I will mention those words again later, okay? So, and of course, the simplest case, which we love, is when it's perfectly insulated. So there's no heat flux on the boundary. That is, phi is 0. So here we make phi 0 here. And so we get this insulated Neumann boundary condition right here. So this is saying, so physically, what is this saying? Physically, this is saying there's no heat flux on the left end of the rod. Certainly, we can specify heat flux on the left end or the right end, both ends, blah, blah, blah. But this is just, the idea of what type of boundary condition we could have for this PDE. We could specify information about U. We could specify information about partial U. These are boundary conditions separate from the concept of initial condition, which is the behavior at an initial point in time. Okay, so let me talk about old Newton's law of cooling. And this has to do with convective heat loss. And Newton's law of cooling here, I've quoted it as it's seen in a textbook. The heat flow leaving the rod is proportional to the temperature difference between the rod and the external temperature. So this makes good physical sense to us. This is the idea of, think about when it's very cold outside and, you put an apple pie that's hot, blah, blah, blah. I don't know. So apple pie, I have no idea. So here we can define the heat flux in this sense. So here, this is saying the heat flux is, so remember, read the equal sign as is proportional to, so you multiply by a constant, proportional to the temperature difference of the rod at the left end and the environment, whatever the rod is connected to. Either it could be a bath or it could just be open air, whatever. So that's literally saying the flux is proportional to the temperature difference. And again, the minus sign is conceptual. Okay, and I'll let you think about that. And I did a little thought experiment here. I'll let you read through that. And so now, again, we can use Fourier's law of heat conduction, to connect phi and a boundary condition. So here, I'm going to replace phi right here, and then solve for u, and that'll give me a boundary condition. So replace phi and then solve for partial u, partial x. We get this boundary condition, known as this, Newton's law of cooling type boundary condition, a Neumann type. So yeah, and at x equal to L, we have to change the sign to match the orientation, flowing to the left, flowing to the right, that type of thing. At the left end, heat's flowing in, at the right end, so I'll let you work through those little details. It's all standard stuff. It's good practice for you also to think about this model. So yeah, that gets us the PDE, the heat equation, and the 3 different types of boundary conditions. And of course, now moving forward, the issues we're going to start addressing are, how do you solve the PDE for these different boundary conditions? And then once we've talked about that, we'll do this all over again, but with a new PDE. The next PDE is, I forget, the wave equation, and then we'll look at Laplace's equation, So this is now kind of, once we've developed the model, we don't ever worry about it. Now we're just going to focus on solving the PDE. Okay, so this is the last slide for this lecture, so I'm going to switch over and talk about thermal equilibrium for about 10 minutes, and then we'll let you go. Okay, so let me switch over. Okay, so now I want to talk about thermal equilibrium. This has to do with the kind of the physical nature of what's happening with temperature. As you're all aware of entropy, I don't need to tell you about entropy. And you can imagine, if we have a heated rod, if you wait for a very, very long time, what's going to happen to it? So that's what we want to talk about here. What happens? How do we model the long-term behavior of the temperature? Okay, so this is where we bring in the idea of what's called a steady state solution, or equilibrium solution. This is a solution that does not depend on time. So this is an extra complication that we have to worry about in PDEs that we don't have to worry about in ODEs, because in ODEs, we don't typically have the time variable, as a separate variable from space. In ODEs, typically the independent variable is time or space, not necessarily both. Here it's both. So we have to think about what happens, when T goes to infinity. And so no matter what the initial temperature distribution of the rod is, some systems will undergo, this physical process that bring it to what we call thermal equilibrium. I mean, as college students, all I have to say to you is cold pizza, right? Eventually it's not hot anymore, or eventually the system finds some kind of equilibrium. That's the nature of our universe, I suppose. And so we expect that thermal equilibrium will be achieved in time. That is, if you take u of xt, the solution, and indeed, hallelujah. If we take u of xt, the solution, and send t to infinity, so this is our solution to the PDE, okay? If we send t to infinity, we expect it to converge to a temperature function that's a function of x only, that does not depend on time, because cold pizza, eventually, it's not all systems. I'll give you an example of a system that does not have a steady state, temperature. But yeah, so here we call u bar of x the steady state temperature. This is essentially the asymptotic behavior of the temperature, asymptotic with respect to the time or temporal variable. U bar of x, you'll notice, is only a function of one variable. So conceivably, we expect u bar of x to maybe be the solution of some type of ODE. That if we took the PDE and took time out of our PDE, it'll become an ODE, and maybe this is the solution to that ODE. So now here's a very subtle part of what we're doing, okay? We want to create a solution that'll mimic reality. So I want a solution, U of xt, that'll describe the temperature at any point in space and time, but I also want, when t goes to infinity, I want U of xt to converge to the steady state temperature. So we make the assumption, okay, so this part's really important now. We make the assumption that our solution U of xt has the following structure, that it's made up of a steady state solution, U bar of x, plus another function that we call the transient solution. So V of xt is also a temperature function, but V of xt is a temperature function that'll decay to 0 as t goes to infinity. That way, when you send t to infinity on both sides, this limit up here will be true. And our solution that's describing what's happening at the present moment will also be a solution that will work when t goes to infinity. It'll also be a solution we can take, the limit as t goes to infinity and figure out what the steady state temperature is. Okay, so now from a mathematical point of view, let's be crafty. What we can do is take this expression and plug it into the heat equation. We can take U bar plus V, just from a mathematical point of view, take U bar plus V and plug it into here. Plug in U bar plus V into U and see if you can't decouple it into a differential equation with respect to U bar and a PDE with respect to V, and we solve each of those separately and put those together. So that's kind of the big picture that we're going for. By the way, not all systems have a steady state, solution or equilibrium state. So consider your blinking holiday lights, right? I think we're 99 days from the winter holidays. Your blinking holiday lights, the light bulbs that are blinking are either on. So when they're on, they're being heated up. So think about the temperature's going up. When it's on, the temperature's going up, or the light's off, right? When it's off, the temperature's cooling down, cooling down, cooling down. And then the light comes back on. So the temperature goes up, and then the light goes off, the temperature comes down. So here, there's no one steady state temperature for this system. There is maybe a long-term behavior, but there isn't a steady, it's not like cold pizza. It doesn't come down to one specific steady state temperature. All right, folks, let's begin to solve a PDE. Okay, but we won't actually solve a PDE. We'll first solve an ODE. So let's do the thing I said. Let's assume time is not a factor. Okay, so here I'm saying assume U does not depend on T, and let's see what happens. So here I take the time variable out of it. So and now there's no more time. Okay, so think about the heat equation. Heat equation says partial U partial T equals the K times the second partial of U with respect to X. Okay, but if it's not a function of time, then partial U partial T is 0. And so on the left-hand side of my heat equation, I have 0. So my heat equation, remember before the heat equation said, let me put this in here. Before the heat equation, we had partial U partial T on the old left-hand side here. But now partial U partial T is 0. Because I'm assuming, because I want to think about, well, let me first solve the equilibrium solution, the long-term solution, okay? So we get this PDE, really it's an ODE, and I divide both sides by K. K is a positive constant, so divide both sides by K. So now I have U double prime equals to 0. Integrate once, U equals, a constant. Integrate twice, U equals this linear function. And so now I need boundary conditions, okay? So suppose the boundary conditions are what we call steady, i.e. independent of time, okay? And suppose just U sub 0 is some constant T1, and U at the right side is some constant here, T2, U at the right side, the temperature at the right side, steady state, and steady state temperature at the left side. Okay. And so now we're just going to do, basic algebra, plug in and solve this thing, right? So if I let x equal 0, if you let x equal 0 in here, this term disappears completely. So this term disappears completely. I just get C2 equals T1 if you let x equal 0. You get C2 equals T1. And so there's C2. Okay, so careful. This is C2. And let's think about where the other term came from. So now, remember C2 here is T1. So let me just replace that. So C2 here is T1. And now let x equal, so I'll finish this and stop it there. So let x equal capital L. So let me replace this x right here with capital L. And on the other side, on the other side we have, here's L. So I've got x is replaced with L, C2 equals T1. And on the other side, we have it's equal to T2. So let me replace the other side with T2 here. And so now, remember what we're trying to do. Don't forget what we're trying to do. We're trying to solve for C1. We don't know what C1 is. So you solve for C1. You get C1 is T2 minus T1 divided by L, which is exactly this term right here. T2 minus T1 divided by L. And remember, C1 was multiplied to X, and then C2 was T1. So here, for this situation, we get the steady state solution has this form. And I went ahead and graphed it. I assumed if T2 is greater than T1, that's what the graph would look like. This would be the temperature profile of the rod at steady state. So here, it's hotter to the right than the left. And here we can also find the steady state heat flux. That's the steady state heat flux. Okay, that's the heat flux at very large time. So I call it phi bar. It's, remember here, time is not, we've taken time out of the equation. These aren't technically PDUs, but these are part of the solution. So this is be the equilibrium solution. Once we find the transient solution, we can combine them, Okay, so yeah, and so we can use Fourier's law of heat conduction and the steady state solution, just take a derivative to also describe the heat flux at steady state. At steady state, we have the heat flux here moving to the left. So yeah, so we've started solving PDEs. And so I'm going to stop here, but you can start to take a look at the examples already. And, you're ready to start just getting into it. All right. So I want to thank you for your time, everybody. Everyone have a good weekend and be safe. And I'm going to stop right here.